Okay, these slides that are coming up are about sampling distributions from our AP Statistics book, and we want to talk a little bit first about some of the vocabulary that we'll be encountering. The first word is a parameter, and we've used it before, but we want to maybe take it in context of this particular chapter. And a parameter is a number that describes a population. So it's not a fixed number, but in practice we don't really know what it is. For the whole beginning of this textbook, we have been doing problems that were very idealistic. We were giving the parameters such as the mu or the standard deviation sigma of the population, but in reality we don't know what that is. It's our job in the statistics is to estimate that to the best of our ability. Then the next thing that we're going to have, and we've had before, is a statistic, and it's a number that we get from a sample. So it's either our it's going to be either our x bar, our mean, or our S sub x, which is our standard deviation from our sample, and then that's going to vary from sample to sample. Okay, so looking back at what we've done so far, I want to make sure that we use the correct notation in this particular chapter, since we're using both parameters and statistics. Remember that statistics comes from samples, and both start with S. Yay, that was very simple. Remember that parameters come from populations, and both of those start with P. The Greek letter mu, which is what we're going to use for the mean from a population. So when you see that, you know that we're inferring something about the population when we're talking about the mu. X bar, from past problems that we've done, we know that that comes from the sample, and that's going to be your average or your mean from whatever sample you happen to have. Sigma, the Greek letter sigma, it's lowercase. It represents the standard deviation of a population. Once again, these are mu and sigma are idealistic parameters that we're going to estimate based on our samples. And then finally, S sub x represents the standard deviation from the sample, and you've seen that in your graphing calculator. Okay, sampling variability. One of the main focuses of this class is to figure out something about the population based on our limited experience and our limited availability in our samples. And we know that if we take a sample and we've had M&Ms and we've looked in the packages before, and we've seen that some people have more blues than others, even in the same size package. And when we're measuring something like that and it continues to vary from sample to sample to sample, that's called sampling variability. And that's okay. We understand that that's going to be the case. But what you need to understand is that the more that the smaller something is, the sample size, the more variability that we're going to have. One of the previous statements from the M&M's company said that about 24% of their M&Ms were blue. Okay, so if we gave every student in class a bag of M&Ms, some students will have no blues at all, some will have over half of them will be blues, and then some will have about 24%, which is about what M&M said. If we do enough of these samples, we'll see that more people have closer to 24% than they do having none at all or more than 50%. All right, so that sampling variability will appear. It is natural, it's normal, but you have to remember that the larger our sample size and the more samples that we take, the closer that we'll get to the true mean that is being predicted in this particular case by M&M's at 24%. If we did not know that it was 24%, we could look at the histogram that was formed from the data that we collected, and right in the middle is going to be our average, our mean. And if we've done everything correctly, if our sample sizes are large enough and we've taken enough sample sizes, then what's right in the middle should be a pretty good representation of our true proportion of blue M&Ms. So take a look at the histogram over to the side. I took the labels off of it because this is kind of representing what we have here. It's normal, it's symmetric. We do see that there are extreme values to the left and to the right, but the majority of your sample means in this particular case, or proportions, will be right in the middle, so that we can get a good estimate of what that true population proportion or mean is. Alright, so in sampling distributions, in order to get a better estimate of the true proportion of the blue M&Ms in this particular case, you had to do the following. You had to take a large number of samples. Alright, so just if we have 35 or 40 students in a class, that's really not enough samples. When we're talking about a good sampling distribution here, we're talking about hundreds of samples. And the idealistic definition of a sampling distribution as we see at the bottom of this particular screen, is that the sampling distribution of a statistic is the distribution of values taken by the statistics in all possible samples of the same size from the same population. So let me give you an example of that. Suppose you went out on campus and you were going to interview 10 people, and I sent the whole class out. I said, each one of you, I want you to interview 10 people. Some students will interview some of the other students that someone has already else interviewed. If we were going to exhaust all the possible samples, you would interview 10 people every single time until there were no other people that had not been interviewed before. So even if you went and interviewed a sample size of 10 and 9 of those people had been interviewed before, but you got one new one, that's still a different sample. And until you exhaust that and you're interviewing 10 out of 10 that somebody's already has interviewed, then that is your true sampling distribution. Okay? So what you would do is you take all of those values that you've collected and you put them in a histogram, and you want to look at the shape, center, and spread, and if there are any outliers in these particular cases. If your sample size is larger, you won't see as many outliers as if you have a smaller sample size. Okay, sampling distributions and sample sizes. Just as we learn how the law of large numbers improves our estimate of our probability, larger sample size helps us improve our estimates of mu and sigma. Think for a moment about the likelihood of extreme means or proportions in small samples, like not getting any blues or in the M&Ms 24 or more. Now think about that. If we had a really large Costco size bag where it had thousands of them, would you expect to have about 24% of the blues in there? If you looked at lots and lots of those bags, it'd be very unlikely that you would have 0 blues or that would be all blues. It would be closer to what M&Ms truly said that the proportion of blues would be. Okay, so the larger the bag of M&Ms, the more likely that we would have their true proportion. Okay, so notice the yellow text at the bottom. The larger the sample size, the less likely that we'll see extreme values or examples of a mean or proportion. Okay, here are 2 histograms. Both of these were the samples were taken from the same population. On the left, you see a sample size was 100, and on the right, you see the sample size was 1,000. Notice that the scaling is the same on both histograms, but the histogram on the right is much more compacted together. If you were to ask someone where the center was on the right side, definitely going to be 0.37. If you looked on the left side, yeah, it's 0.37, but look at the spread. We have all the way from 0.22 to 0.52. Over on the right, we don't have that. And that's just one of the things that a larger sample size will provide us. It gives us a much more compact, less variable histogram or distribution. Okay, now let's talk about bias of a statistics. Earlier we had talked about the bias of a sampling methods, and then that was the systematic favoring of one outcome over another. Well, the bias of a statistic, okay, not a sampling method this time, the bias of a statistic is an overestimate or underestimate of the parameter that we're observing. So if we're looking for mu or proportion, if we're overestimating or underestimating because our sample sizes are too small or because of poor survey techniques, we encounter that bias. And so we say that a statistic is unbiased if it's a great estimate of the parameter that we're looking for. So if we're looking for a mu, and if we look at our sampling distribution, and right in the middle is mu, and it's what it's supposed to be, then we know that it's unbiased. The variability of a statistic, hey, it's natural, it's going to happen. It's described by the spread of the sampling distribution, and we saw the 2 histograms earlier. One had a really large spread, the other did not. And in this case here, as I said earlier, larger sample size gives smaller spread. Now here's a little rule that we have to follow down at the bottom, and it says as long as the population is much larger than the sample, say at least 10 times as large. We could fudge that a little bit, but we like to go for populations that's at least 10 times as large as our sample size. So if our sample is 20, then we're looking for a population that's at least 200. Okay, if that's the case, then the spread of the sampling distribution, okay, the spread of the sampling distribution is approximately the same for any population size. Okay, and that's going to be one of the rules that we have to follow and one of the checks that we have to make later on in the semester. Okay, the last slide here that we have here are some examples of variability and bias. Notice in the upper left-hand corner, the variability is, these are all like targets, all right, and the variability in A is low. All of the little shots or the dots are close together, but it's nowhere near the center. So it's got a high bias because it's away from the center, but low variability. B, it's low bias and high variability. Notice that it's really spread out. All right, so but it's all gathered around the center. So we can kind of pick out where the center would be. So the bias is low. We can estimate where the center is, but it's a high variability. Okay. On C, we look at high bias and high variability. It's really spread out and it's really far away from the center. So it's really difficult to tell where the center would be in that particular spread. And then D is ideal. It's very close together, so it's low bias and low variability. It's right on the center and it's clustered together. So this is what we are shooting for, and then this was going to give us our best estimate of our parameter. I hope this presentation is informative. Please go ahead and take a look at the problems that were assigned to you, and if you have any questions, you can ask them in class at our next meeting. Thank you.